we're going to look at why don't companies save your password? And if they do, how they put you at risk. Now, this isn't a problem limited to small companies. Companies as large as Google, Facebook, Twitter, Robinhood, and even GitHub have been caught saving passwords in plain text. So why is this such a big problem? Well, let's say you've created an account with a website and a hacker is able to get your password from that website. Obviously, they could use this to log into your account, but this isn't where the problem stops. Up to 52% of users use the same password for multiple accounts, and there's some that use the same password for all of their accounts. So this means the hacker could use that to possibly get into their banking software, into their Twitter account, or even go on a shopping spree on their Amazon account. Now, just for reference, the average email account has about 130 accounts tied to it. So most of these accounts, the user probably doesn't even remember, but it doesn't mean they're not vulnerable to that hacker's attack. Now, this isn't a video on SQL injection attacks, and there's actually multiple ways passwords can get out. But in short, if a hacker is attempting an attack, they might use, say, a login request where they're adding some extra text to change that SQL, that query that's going to be run on the database. So basically, when the website's checking to see if the username and the password match, the hacker's going to attempt to change that query to get back the information they want to get back. Now, in actuality, if a hacker is able to get a username and password, they're probably just going to take all the information in that table. So they're going to take all the usernames and all the passwords. So in the past, there's been cases where companies have compromised, had millions of usernames and passwords compromised, and that can be a serious issue. For instance, the hacker could compromise, a lot of these accounts one by one, but if there's a lot of them, very likely they're going to sell this on the dark web as well. And so a whole bunch of hackers are going to get their hands on it, and who's not to say that those hackers aren't going to give it, sell it to other hackers. So in short, once that data gets out, it's not coming back. It's gone. It's just going to keep spreading. Also, these could also be added to a future dictionary attack, just making the hackers even that much more effective. So this is where hashes come in. So in our original example, we had the database saving the username and the password in plain text. So if the hacker is able to get that username and that password, they can just enter the username and the password in the login form, and they're going to be logged in. Now, hashes are going to be a little bit different. So if we're saving a username and a hash, obviously if the hacker steals that hash, they can't just put the username and the hash into the password field. Well, that login is going to fail. So it's hard to come up with a good analogy for hashes, but let's say basically we don't want to hold on to that password. We just want to verify that that password was given to us. So I guess a good analogy would be if someone had the recipe for Coca-Cola. I don't need to know, if I want to know that they're that person, they don't actually have to give me the recipe for Coca-Cola. They could just create a bottle of Coca-Cola for me and I could taste it, be like, hey, yeah, that is most definitely Coca-Cola. That's not Sprite, that's not root beer, that is Coca-Cola. And that's a one-way process as well. By tasting the Coca-Cola, obviously I'm not able to say, hey, these are the exact ingredients. I can't reverse it or take it back. Same thing with a hash algorithm. So we can take a password, run it through our algorithm, we can create our hash. It's very difficult to take this hash and just take it back to the password. So how do we use this with our website? When someone registers, we're going to take that password, run it through our hashing algorithm, take that hash, save it in our database. So the next time they want to log in, they can give us that password again. We run it through our hashing algorithm, and then we can take that hash from that login, check it versus the one in the database. If it matches, we can log them in. So this is going to create an extra step for the hacker where they're going to have to find a way to change this hash back to a regular password so they can try and log in. Now, one of the problems we're going to run into is the lack of randomness from our users. This is a list of the most common passwords from Wikipedia. As you can see, from 2013 to 2019, the most popular password was 123456. And you're going to see a lot of just, not a lot of randomness here. You know, password is going to be a very popular one. There's going to be a lot of these you're going to see in the same place, like baseball and football. You're going to see in many different places. And this is going to create a problem for using hashes. So now that we're using a one-way function, are we good now? Obviously, no. So we're going to have to go a step further. I'm going to explain why. So we have our username. We've created our hash. The hacker could, once they've stolen this from the database, they can usually find the password by running it through a dictionary attack. So a dictionary attack will be where they take a lot of the popular password and combinations of passwords and popular symbols, and they're going to go ahead and run a hashing algorithm on each one of these. So this was a real popular password, 123456. They run the hashing algorithm on it, and we get this hash here. So they're checking it versus this hash. Is it the same as the hash that we stole from they stole from the database? No, it is not. So they'll go and they'll run another common password, and it will give us this hash, and they're going to say, hey, is this hash the same as that hash? No, it's not. Let's try another one. And eventually they're going to try, for instance, in this case, password 1, and it's going to give us this hash. It's going to check it versus that one. It's the same one. So now they know that password 1 was the password, and now they're going to be able to get into that account. Now, one thing to keep in mind, this SHA-256 is a very fast to run hash, and that is not advisable. You want something that takes a little bit longer. If we use a longer hashing algorithm, let's say if we're logging in, the user's logging into our, their account, if it's a few fractions of a second longer, they're not going to notice or mind. But if I use a longer hashing algorithm, or and the attacker has to use that, well, since they're going to be checking tons and tons of possibilities, that's greatly going to weigh at their expense. It's really going to take up a lot of their time and make it a lot harder for them. Now, this is where rainbow tables come in. So like I said, it does take time to run that hashing algorithm, especially if you're going through many, many, many possibilities. A rainbow table is a table of many passwords and hashes. So this way, they don't take the time hit for running all these algorithms multiple times. So they can just run each password through the algorithm one time, save that result, and once they have this humongous table, it's going to be a lot more performant for them. They're going to save a lot more time using a rainbow table to just check and say, hey, is this hash the same as that hash I was looking for? And if it is, then they'll, hey, this was my, back one. Then they'll know this was our password. Now, the trade-off here is that they're going to be trading time for memory, or for storage. So for instance, right now, a rainbow table could be a few gigabytes to a few terabytes. And if a hacker is trying to crack several passwords, well, it doesn't take a whole lot to store a few gigabytes or even a few terabytes. A lot of people could get access to that very easily. So, another problem with the lack of randomness, a lot of the popular ones are going to be stored in these rainbow tables. So you imagine a few terabytes, that's a lot of different possibilities saved in there. So to combat this problem with the rainbow tables is we're going to go ahead and add some randomness into the hash ourselves. So we're going to use what we call a salt. And a salt is just a random sequence of characters. So we have our random characters here. This is our salt. And to create our hash, we're going to go ahead and take our salt, add it to our password, and now I have this random sequence of letters, password 1. When I run the hash for it, I'm going to get this hash here. It's going to be very unlikely that a hacker is going to have a rainbow table with this random, where every single one of these combinations, had this random sequence of letters in front of it before it was hashed. So the likelihood of them having a rainbow table for that is just, very, 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 very small. Now, it's important, and so, like I said, with a specific input, we get a specific output. This will always have the same output. Now, being that each one of these has a unique salt, it's going to have a different output. So, say if they run through a dictionary attack, they can't just save all of the hashes and expect it to use it. Say if they crack Carl's password, they can't use that to crack Jane's without starting over again, because by putting a different salt on the front to create that hash, well, they're going to have a whole different rainbow table for that. So, I mean, they could create rainbow tables, but it would just be an astronomical amount of rainbow tables, and it wouldn't work. So, they want to make sure that this is unique, so that way, the hacker can't just reuse all those hashes that they've created, in search of a different password. So, by adding a different salt to each one of these, they basically have to try and run it all over again for every single user, which is going to increase the time required, exponentially. Okay, and cost. So from year to year, hardware performance, and software too as well, but hardware performance is always getting faster. CPUs are getting faster, GPUs are getting faster. A lot of these hashing algorithms were once run on CPUs, now they can be run on GPUs, so they can get a lot more done. There's a lot more cores in a GPU. It almost sounds a lot like the cryptocurrency mining craze. It was done on CPUs and it was done on GPUs, and eventually, they went with dedicated hardware like ASICs, which is extremely fast. I don't know if they have that. I don't know if they're creating dedicated hardware yet for hashing, but the point being that this stuff is always getting faster every year. The hardware is always getting better. So that's where cost comes in. So if we want to use a hashing algorithm, that's we can use into the future, we're going to need something with a parameter or a argument called cost. So we need to be able to make it more complex and more intensive to hash it. So by changing this cost in our hashing algorithm, we can make it much more difficult to create that hash. So as hardware advances, we can just increase this cost, and it will increase the time required to make that hashing algorithm complete. So anyway, in short, hackers are going to be persistent in coming up with new ways. So it's real important to not, for instance, not save a password at all, because it can always get out, especially if a whole list gets out. You're not just compromising accounts. You could force all users to change passwords on your website, but those users are unfortunately probably compromised on several other websites, being most people use the same password for multiple accounts. But anyway, if you enjoyed the video, like and subscribe. Greatly appreciate any help I get. So I'll see you in the next one.